My name's Livia. The next presentation will be given by Andrew G. Bennett from Kansas State University, and it will be a talk on machine learning for modeling in an elementary differential equations class.
Thank you. Uh, so the idea behind this talk was that our students are reading about AI. Everything's going to be AI. I have a colleague who has told me that, in 5 years, we will all be irrelevant because of AI. And I have said, I'm 65, timing works for me. Um, that wasn't the response he was looking for. But I do think we do want to be looking at AI. It's important for me. I can say, yeah, never use AI. I'll retire before I really have to. That's not true for my students. They need to know how to do this for preparation. This is an active area of research. It will be an important tool long before the end of a student's career. And motivation. Undergraduate differential equations is often seen as a cookbook course that tells you things that people did many, many years ago. And bringing in an active modern area has the students saying, oh, maybe I do need to know this. Um, and what I focus on tends to be more machine learning rather than generative AI, saying if you're a researcher, you're going to be using machine learning as a tool. But I don't primarily want to teach machine learning. I do want students thinking about what are the pluses and minuses? What does this do? So the course I'm working is a little different, I think, from many of you, in that I have a very large course. In the fall, I had 180 students in differential equations. This spring, I have 240. That means that I'm working with half a dozen TAs, and that makes it sort of fun to say, how do you set this up and how do you train all the TAs to know how to do these things with the students? It is well over 90%. I think this term we hit 95% engineering students. But we do have math majors and things that take it. We have a Calculus 2 prerequisite, though most students have had Calc 3. And historically, we've offered multiple opportunities for extra credit, in calculation of variations and things like that. And so the idea was, let's build an extra credit assignment for this. So we usually model a spring mass system. We say, okay, we've got law of gravity, Newton's laws on force and acceleration, Hooke's law telling you what the force is from a spring, and we have damping and friction and air resistance. And I point out to the students, we have Newton's law and we have Hooke's law, and we have, just make it linear because linear works. We don't have a name for how we deal with the damping because there isn't a physical law telling us. So instead of guessing at damping and saying, I'll let it be linear, or maybe I decide that for air resistance, I should be letting it be proportional to velocity squared, why don't we let a neural network trained on observational data decide what damping works best? And so that became the extra credit assignment, to work through a Jupyter notebook to model a spring mass system with nonlinear damping learned from the data. One of the advantages of a Jupyter notebook is that enables us to offload the machine learning parts to built-in libraries. We use TorchDiffEq. It also means the students do not have to do any significant programming. And I was sort of surprised that I could have a class with 95% engineers and such a small percentage of people who knew anything about programming. But apparently that can happen. They tell me that's because programming is the course they take after differential equations. But this way we can set things up where they can work through it, even if they don't have that background. The goals were to improve the understanding of the modeling process, to give them an experience in using machine learning while modeling a differential equation, and to see some of the advantages and disadvantages of both the traditional and machine learning approaches. So the first thing we did was data collection. I would like to thank Peter Nelson, a research technologist in the physics department, who helped a couple of mathematicians who dropped out of physics because it required labs to figure out how to actually collect data, set things up where we could have a spring, mass system. And the students can watch a video of this if they want to see, no, this is real data. You can see what's going on there. And then we used the Tracker app, which is a free physics app that will take a video and you mark something on the video and it will track where it goes. And that enabled us to convert the video to a graph, to numbers, to say this is where the spring was as time passed. So first thing we did was say, let's go look at Hooke's law. And we had attached various masses to the spring and measured the displacement and asked what the value of the slope was, which turns out they need more help than I thought to find the slope of a line. They did a lot of, well, I picked 2 points and the slope between these 2 points. Or I sort of guessed at something. I drew a picture and I drew a line and I sort of measured. I'm thinking you didn't put it in a spreadsheet and ask it for the answer. If you do, you find that the slope, you can find the slope, and from that you can find the spring constant. The R squared for this thing, by the way, is 0.99. If my physics labs had turned out that way, I would have thought more about doing physics. I still would have ended up in math, but I might have thought a bit more about doing physics. And the spring constant turns out to be 8960. And then we said, okay, now let's just fit a decaying sinusoidal to this graph. And wonderfully, the first time we did it, we got this result where we have the graph in orange and the predicted value is the blue. And I was thrilled. We had fixed a pseudo-random number generator so that all the students would get the same thing out. The neural network populates with the initial parameters are chosen randomly. We didn't want to have different students getting different results and are having to grade to figure out what's going on with the different things. So we had fixed a pseudo-random number generator. And as you can see, it did very, very badly. This is a case where you have a vanishing gradient. So the way machine learning works is you fill in all the values, you run the system, and then you say, okay, what's the gradient for each of these different things? And the gradient turned out to be near zero, and it just settled down into nothing. And I think that's terribly important that they realize this can go wrong. And it can go wrong just randomly. That you may need to do these things multiple times because you might get caught in a local minimum and you need the global minimum. Indeed, typically you're going to have a situation where you will not know that you're in the global minimum, but for many situations, many of the local minima are close to the global minimum and you can get by with it. But that's explicit in the machine learning literature. So then we just had them change the seed. So say you've got the code, go in and change which of these lines is commented out. And now we get a very good fit. Not perfect. It's clearly overshooting a little and undershooting a little. It's trying to sort of manage that to say, how can I make it come out okay over the whole thing? But we get a fairly decent fit. And this is for the traditional value of just saying, just assume that it's a decaying exponential. Whoops, hit the wrong button. There we go. And then we asked them to find the spring constant. After all, if you've got the decaying exponential and you know the mass, then you know the spring constant, And when they did, they found that the spring constant was 8087. But we had measured it. We had an R squared of 0.99 and had 8960. It is I gather I'm not the only one who has trouble with physics labs, because a lot of the students took the viewpoint that said, oh, well, then I obviously measured wrong or something. The data you gave me is obviously fouled up, or there's something. The computer has a line that says 8960, that must be right. Or 8087, and that must be right. And it took a little to explain to them, no, the correct answer is 8960. The computer's close. It's off by about 10%. The linear model's not bad. When you look at the picture, it's pretty good, but it's not perfect. It's not great. We're off about 10%. There's probably room for improvement. What could we do? And that's when we put in and say, okay, let's try fitting a nonlinear model. So what we did was put in mx double prime plus fx prime plus kx, where f is the output of a neural network trained on the data by gradient descent. And we have the Jupyter notebook set up. The way this does it is it picks an f, solves the differential equation numerically, compares, goes back, figures out the gradient of how each of the different little parameters in the uh, neural network affected the loss function over the whole thing, updates those parameters, runs it again. After about 100 runs, we got to where the loss function had stabilized to 4 digits. The biggest thing the students noticed is that took 20 minutes. And the students are used to the notion of I type something into the computer and something happens. If it takes me a minute to get a response, I'm complaining about how long it takes to get a response. And the notion that 20 minutes, and in the Jupyter Notebook, it says specifically, this is going to take 20 minutes. They don't believe me. After they've done it, they realize this took 20 minutes. And this is for a toy problem of just one little spring bobbing around on one little equation. I see Kurt's in the audience. I did give this talk earlier, and Kurt wondered if adjusting some of the hyperparameters of the model might speed things up. I've gone back and done some of that, and the answer seems to be no. That doing things that I thought might improve this, it just takes a while. This is going to take a while, which I think is good. But then we can compare what did the model predict the fitting a decaying sinusoidal. What did that predict was the damping in blue? What did the neural network find? And you can start to see why is it that we think that a linear model is going to work fairly well. For a reasonable range of velocities, the linear model is very, very close. Of course, that's the fundamental idea of calculus, isn't it? That if you restrict to a particular range of a curve, you can do really well with a line. On the other hand, when the velocities get higher, which may be why when we're shooting things, rockets in the air or something, we tend to use v squared. Well, if you're bobbing a lot and fast, now you start to see more curvature in things. But they can see, oh, I see how the damping works. I see why this goes. And we can ask them, explain this to us. Tell us when you would use what. But they have worked out, here's how the damping really goes. And we can discuss with the students, so how much extra effort is needed for the nonlinear model produced by machine learning? You had to get a bunch of data. And they're very aware of it took me 20 minutes. You talk to them, that's a big thing. Do we need any differential equation? Could we just throw data into a model entirely? Have a neural network predict things. And I don't know that we do a good job of explaining that well, but I have a grad student. As I said, I have to work with grad students to manage all this. I have a grad student tomorrow doing a variation on this that he built up that does a better job of addressing that middle point. One point we do try to point out, if you just have the neural network, could you distinguish that there's underdamping and overdamping? Would you recognize there are qualitative differences that come out? We can see that if we have the formulas that we get from a linear model. And if you just use the neural network, you may say, I know exactly how this spring behaves. But are you going to know how some different spring behaves? What if there's a qualitative difference? Can you recognize those sorts of phase changes? And so there is a point to having the machine learning, but also to having my course. There's a point to having my course. So the final question we ask them is to say, okay, you're an engineer. One of our examples is a two-tank continuous stirred tank reactor system where things flow into one tank, they get mixed up, then they flow into a second tank, then they flow out. Uh, Here in Kansas, we talk about ag runoff and things and how you use holding ponds for stuff, which is the same sort of setup. And like every book I've seen, in that model, we make the usual simplifying assumption that there is perfect mixing. As soon as you add anything to tank one, it spreads evenly through the whole thing. Well, that's not true. But suppose you're asked, somebody comes to you and says, I think we can do better by using, neural networks and things to better model how contaminants flow through the tank. What are the advantages and disadvantages? And we can look at their paragraphs and say, did they recognize I'm going to have to find data on where the contaminant is in the tank at different points? I'm going to have to set up this, and now it's going to be more complicated, and I'll have a spatial component, and my gosh, how long is this going to take me? And how much better is it going to be? The fit with the nonlinear damping is better, but is it enough better to make it worth all the work you're doing? And as an engineer, you may want to say, yeah, we could do that. It's going to cost this much, and I don't think it's going to improve matters much. Or maybe you'll say, yes, we can do that. It'll cost you this much and keep us busy for a while. But have my students thinking about this is where these things go. The student reactions are mostly positive. I like the quote of it provided a taste of the sorts of tools that will be developed for you to use as you continue in your careers. That after the assignment, it was an extra credit assignment. It was popular. 105 of 170 students did it. They were interested in saying, I'd like to see how this stuff works. They're also interested in getting one test question's worth of extra credit was the amount we assigned to it. And afterwards, we offered all students one additional point, including the students who didn't do it, just to write a response about what do you think about AI and this sort of assignment. 70 of the 105 students who did it turned that in. So I have a reasonable confidence we've got a sense of how the students felt about it. They did like it, but the students think of machine learning and AI as magic. I type a question into the computer, I wait 30 seconds, and it solves my problem for me. The notion of I had to do all this, that is new to them, to most of them. They have started thinking about it, particularly the better students. There's a clear correlation of did you start talking about ethical issues or environmental issues and how well you're doing? The better students have started thinking about this already and have gotten some fairly deep ideas about AI. But this was new to them of, okay, this is what it really looks like. Looking back at the
Just a
goal.
heads up, sorry, you only have 2 minutes left of the talk.
Okay. As I said, based on those note cards, we think we were successful in improving their understanding of the modeling process. Obviously, they did get an experience, well over half of them. And their answers to the question about the continuous stirred tank reactors showed they were starting to develop an understanding of, okay, I've got some notion of what this does for me and what it doesn't. Some variations that I might use if I were teaching this in a class of 20 instead of a class of 200. You could have the students collect the data themselves. The tracker app's fairly straightforward. And once you know how to set things up and get it so the thing bobs and doesn't bump on things, you could have them do that themselves. That didn't work well in a large lecture, just to do it. I did collect 25 runs. We only used one of the runs. If I really wanted them to better understand the modeling process, I'd do a full train, validate, test cycle and say, here are 15 runs of data, test, build on that 15 runs of data, then validate against 5 runs of data till you're sure you've got the hyperparameters right, then test on the final 5 runs of data. That's a week-long project. That's not a, hour or two extra credit worth one test question, but you certainly could do that. And finally, if you're in the right situation, you might have them do more of this is how you set up the coding. This is how you get the Python libraries in place to run the machine learning. As I said, I was surprised at how few of my students were prepared for that. But if you had students who were familiar with Python and using things, that would be fine. But I have some questions for you. How much do we want the students to code? How much do we want to address machine learning and AI in our classes? And one thing, what should the rules be? Because it turns out we distributed our notebook with Google Colab. Google Colab is set up so Google's AI assistant Gemini is always available at the touch of the button. I can turn it off on mine, but when I put it in Colab, when they go to it, it pops back up. I can't turn it off on other people using my thing. And it turns out that if you ask Google Colab, you ask Gemini, can you answer the question in the current cell? It does pretty well. If you ask it at the beginning to do the whole thing, it gets lost because you go through and it says, oh, this worked wrong, go back and change that and run it again. And at least as of last fall, Gemini didn't do that well. But if you walk through step by step, Gemini gets an A. What should the rules be on this? And is there any way we can enforce them? And I'm not certain where we go on this, but it's going to be interesting. So, as I said, thanks to Peter Nelson for advice and help on data collection. Are there any questions?